Welcome to the lecture on heat affected zone, that is when we talk about the fusion welding processes, then we discussed in the last class that you have the distinct zone formation, and among the distinct zones the heat affected zone, which is also known as HAZ. This is of paramount importance because in certain metals typically where the allotrophic transformations take place. So, in those cases what we see, that we see microstructural changes taking place because the material is subjected to the thermal treatment, a kind of heat treatment, and so that affects the mechanical properties. So, we will talk about the heat affected zones in this lecture. So, as we have already discussed that heat affected zone is that part of the welded joint which is heated up to the solidus temperature of the parent material. So, the temperature may go up to the solidus temperature in that because in the middle part you have the weld metal zone, and then once you are coming near the fusion boundary zone, there basically you have unmelted grains. So, basically you are coming till the solidus temperature. So, from there the heat affected zone starts and it goes inward towards the parent metal. So, now because you have the heating and cooling cycle, so in that case you have the varying degree of influence on the macrostructure, and further if there is effect on the macrostructure, then there will be effect on the mechanical properties, because mechanical properties are related to the microstructure. So, depending upon the peak temperatures which are achieved, we get to know the different zones of even the heat affected zone. So, it is basically subdivision of the heat affected zone, and as you take from the temperature in decreasing order. So, you will have initially the underbid zone, then you will have the grain growth zone, then further you will have the grain refined zone where the recrystallization is basically taking place. Further down you will be having the partially transformed zone, then you will have the zone of spheroidized carbides where the temperature basically is somewhat lesser, and then how the cementite is changed to some other shape, spherical shape, and then ultimately towards the end you have the zone of unchanged base metal. So, these are the different regions which we discussed in our earlier class also. Now, before that as we have seen that in the case of welding, as you know that it is something like when we call we relate it with the heat treatment process, but there are certainly some basic differences between the welding and typically the heat treatment process. So, if you talk about the difference of these two processes in welding, as we see, we go to higher temperature. We take the example of steel. So, we are going till the solidus temperature. So, maybe close to 1400 degrees C we go in case of welding. Whereas, if you talk about the heat treatment processes, then normally we are going to smaller temperature, we go little above the upper critical temperature. So, somewhere we are going maybe some degree, 100 degree, 50 degree above that temperature, we are going into the austenitic range, and then we are further cooling. So, the peak temperature which you are achieving in these two cases are different. It will be higher in the case of welding, and it will be on the lower side in the case of heat treatment. Then next is the retention time. So, if you talk about so the difference between the, so you have the parameters like peak temperature which you are achieving. So, that is the difference. In welding you are going to about 1400 degrees centigrade, and in heat treatment we are going close to 1050 degree centigrade. Then talk about other parameter which is important is the retention time. Now, retention time means when you go to the peak temperature, then how much you are retaining there, for how much time you are there at that temperature. So, in welding basically that is very less. We are not we are not staying at that temperature, that is very less. But in case of heat treatment we try to we go to that temperature and then you allow the material to stay at that temperature for some time, and then you are going to cool it. So, the first is peak temperature, second is retention time, and third is the cooling. So, if you talk about the cooling rate, then cooling rate will be quite high in the case of welding, whereas in heat treating you have the varying cooling rate. So, if you talk about quenching, faster cooling, there certainly the cooling rate is higher, but otherwise you can have the smaller cooling rate like annealing or so, or even air cooling. So, that cooling rate is also that is controllable in the case of heat treatment. You can have higher, but otherwise it is on the lower side. Whereas in the case of welding the pool is very small, the liquid metal is very small, and it is surrounded by very conductive material. So, it is cooling fast. In the case of heat treatment you are basically heating the whole material and then it is subjected to cooling. So, that is the difference between welding and heat treatment. So, you have also if you talk about the heating rate. So, in the case of if you talk about the heating rate, so heating rate is also higher in the case of welding, because you are putting the amount of heat that is able to melt it quickly. So, you have case of very high heating rate and very low retention So, and then you have further cooling, so quite high rate of cooling. So, basically very high heating rate, low retention time, and then further cooling, that leads to the non-homogeneous austenite formation normally in the case of welding, that is the trait of the welding process, and because it subsequently gets cooled. So, you will have the localized regions of martensite, that is high carbon martensite, which is formed in the case of welding. So, when you take the macro hardness in a welded specimen over a range of area. So, in that case you get a range of macro hardness values in a welded specimen. So, that is what you get in the case of so that is basically the difference between these two processes. Now, coming to the different zones which we talked about, the heat affected zone. In that zone, so you can have a look at this heat affected zone in the case of ferrous material steel. So, here what we see, on the right hand side we see the iron carbon diagram. So, and we can have a feel about the different zones which are formed in the case of the steel. So, what you see, this is your iron carbon diagram, what you see, this is your alpha iron, and then you have this is your gamma iron, in this side you have delta iron, you have liquid, and so you have above this temperature you have all liquid. So, once it comes below this temperature you will have some solid plus liquid zone will be formed. So, as you see from in this to this so for this composition of steel you will have from this zone to this zone you have, that is solid plus liquid. So, and then after that so based on that basically you have different zones which are shown. Now, this is the temperature, this zone is known as the grain growth zone. So, because here the temperature is towards the higher side. So, in this zone your grain growth is predominantly taking place. So, that is your grain growth zone, then you have the recrystallization going on. So, based on that you have the grain refined zone or recrystallization zone. You have the partially transformed zone. So, that is normally between the critical temperatures. So, for that you have, this is your partially transformed zone, and then you have other zones where you have the zone of spheroidized carbides, and then that is this zone, and then you have the zone of unchanged base metal. So, that way you have the different zones which are formed. So, the first zone which is typically there. So, after you have the melt metal zone, and after that you have the once you go towards the base metal. So, where the weld metal zone ends, you have the fusion boundary. So, you have the fusion zone. Now, after that you have the underbid zone. So, below the bead you call it as the underbid zone. So, your next zone becomes underbid zone. So, this zone, the characteristic of this zone can be understood by its placement. So, it is just under that bead position. So, it is next to the fusion boundary zone. So, certainly, because in this case the temperature as you see that it will be just to next to that fusion boundary zone, and you can also have. So, here this undergoing, it is undergoing that austenitic transformation, because in that case the austenite is getting transformed, and also because of the very high temperature, certainly the growth is also one of the phenomena which is prevalent there. So, in every fusion welding process you will have a zone where the temperature is higher. So, you will have the growth of the grains. So, you have the underbid zone, and that zone, as you see here. So, you will have, as you see, this is your solidified weld, and then you will have this solid liquid transition zone. So, that that tells you about the placement of that. And normally what we say, so if you try to define these underbid zones. So, we have already talked about the temperature where this, so it is going nearly this 1400 degree centigrade. So, if you refer to as we discussed, that if you refer to this, so you will have the underbid zone, which is basically just below this range, and it will be taking care of two zones. It will be taking care of so it is above the critical temperature of grain growth, which normally occurs in the metals at certain temperature, and it will be varying upon the steel composition. So, that there will be certain value of certain temperature value of the critical temperature for grain growth. So, that so upper limit will be going towards that fusion boundary zone, and on the lower side it will be coming up to the grain growth zone, because you will have a critical temperature for grain growth. So, that temperature will be the lower boundary for that underbid zone. Now, as we discussed that in this zone you will have so that basically the grain this underbid zone, you will have certainly you will have the grain growth which will be taking place in that zone more predominantly. And certainly there are many disadvantages because of the grain growth which is taking place in the case of metals. So, and those disadvantages are like you have if you have the coarse grains. So you may have the challenges like decrease zone plasticity. Then you have the slowing down of austenitic decomposition. So basically sometimes that favors the ferritic formation or ferritic precipitation, and you have some different type of microstructure is also formed. So so that way that is the outcome of the coarse primary grains. Then you have also, if you have the growth of the grains, then you have increased susceptibility of steel to cold cracking. So that is another disadvantage with these grain growth zones. And then you have also the lowering of strength. So you will have the lowering of strength of underbid zone. In metals which do not go the polymorphous transformation, like the aluminum or copper or nickel. So there, when there will be growth of the grain size, then in that case it will be resulting into the lowering of the grain sizes. Now as we discussed that this critical temperature of grain growth. So you as you know that in this case we are talking about the zone which is below that fusion boundary zone, next to the fusion boundary zone. So now it will be depending upon how much there is growth, and that depends upon the critical temperature value of the grain growth. And the critical temperature of grain growth, it has normally the value of this is 1050 degrees centigrade for normal carbon steel, whereas for carbon steel, and for if you go for microalloyed steel. So for microalloyed steel that is going till the order of 1350 degrees centigrade. So this way when you your temperature of the for the critical temperature of growth, grain growth is higher, in that case the grain growth will be somewhat smaller, because the order of temperature which is going above that temperature, that will be smaller in these cases. So for these microalloyed steel, where the steel is basically microalloyed with certain elements which are strong carbide formers, or which are basically used to refine the grain structure. So in those cases your critical temperature of grain growth is very very high, and in that case your grain growth will certainly be at somewhat lesser level. Now it will also be, the grain growth will also depend upon the composition of steel. So if you say, so see that, so the grain growth also depends on composition of steel and specific heat input in welding. So in the different welding processes, we provide the different specific heat input, and if you talk about the SMAW process, shielded metal arc welding processes. Now in these cases the growth expected is small. So you have here you get small grain growth. Then from as compared to SMAW, in SAW it is more than SMAW, and if you talk about the electroslag welding ESW, even it is quite high in those cases. So, the grain growth phenomena is seen to be more prominent in those processes. So, basically it also depends upon the type of welding process, that is specific heat input in the welding, because it is less in the case of SMAW. Then you have the SAW, and then you have certainly the ESW. So, accordingly your that grain growth which is observed will be changing. Next, if you talk about the next zone which is formed, which will be there below that grain growth zone. So, you will have the recrystallized zone, or also we call it as the grain refined zone. So, in this zone the grains are refined, grain refined zone. So, because of the recrystallization process in this zone you will have the finer grain structure. So, towards the so in the upper side where in the grain growth zone the temperature is higher, and once you come down in that case you will have so if you talk about the gamma to alpha transformation on cooling. So, normally they will be providing your fine ferrite perlite structure that will be depending upon what is the heat input or what is the plate thickness. So, based on that you will have so basically you are going to that temperature. So, once you come towards the base metal side. So, if suppose this is your this is your weld metal zone, and then this is your different zones of. So, initially you will have the fusion zone, and then you have the underbid zone, you have grain growth zone, and then after that this zone. So, in this zone basically your temperature is heated, and it will go maximum to maybe 1100 or 1150 degree centigrade, that will be maximum temperature. Now, above that you have normally the grain growth range. So, so there the growth takes place, but in this zone you are heating and you are going into that zone, and then from there it is the temperature is coming back. So, basically you are heating to so when you are heating you have so while heating you have alpha to gamma transformation, and it does not have you don't have you don't give them sufficient time for the development properly. So, your grain size will be remaining small itself, it will not grow. So, so that way in this case your grain size remains smaller. All the carbides which are there, they are not completely dissolved. So, so because anyway in retention is very small in the case of welding. So, your all carbides are not fully dissolved, and when you go for the as we discussed, then when you go from gamma to alpha transformation. So, you will have the fine grained ferrite perlite structure which will be formed in these cases. Now, the grain boundaries, the large grain boundaries, they will provide so they will be promoting the ferrite nucleation on the grain boundaries, and austenite will be remaining at the grain centers in such a cases. So, normally for the this zone is it's basically it is useful when we talk about the microalloyed steels, because this zone is quite wide in the case of microalloyed steels, because the effective the effectiveness of the carbonitrides in preventing this grain growth will be there at these temperatures. Normally at the temperature of 1150 or so you will may have the experience of grain growth, but when your carbonitrides are there in those microalloyed steels. So, they restrict the further grain growth. Now, the next zone after this the grain refined zone, The next zone in that will be your partially transformed zone, and basically this zone the grain refined zone. So, it will be starting from the value of upper critical temperature, and it will go maximum to 1100 to 1150 degrees centigrade, and after that you have the zone of partially transformed zone. So, you have partially transformed zone. So, this zone in this zone is characterized by that zone in between the upper and lower critical temperatures. So, basically this is a zone. So, for this composition, this is your upper critical temperature and this is your lower critical temperature. So, this zone is basically that zone which has is there between the critical temperatures between A1 and A3 temperatures. So, normally you will have the range of from 750 to 950 degrees centigrade. So, that kind of you have the temperature range where which is signifying the partially transformed zone. So, you will have the eutectic perlite which is there. So, they will be beginning to dissolve when they are heated beyond this temperature. So, in this case normally what happens that you are getting a chunky perlite type of structure in such zones. So, now the thing is basically because of as you know that you are heating, you are going into that temperature range, and then you are the temperature further comes down. So, there is not much of the time. So, as as you go above the A1 temperature, then your eutectic perlite will start dissolving. It is twite perlite basically, and then basically and then quickly the temperature will start coming down. So, the carbon will so that there will be failing of the carbon to further diffuse back into the former perlite grains. So, that way you have the formation of the chunky type of perlite. So, in this case you have chunky perlite structure which is there, and many a times this intercritical that leads to a dual phase type of structure. So, when we do the higher speed of cooling, so the former perlite grains can be quenched to martensite. So, the extreme case you may have the dual phase type of structure, that is ferrite and martensite type of structure, that is forms. So, dual phase steels are very much used. Basically they have the ferrite plus martensite, that is dual phase. So, that kind of structure is likely to be obtained. It has very good strength. So, that way they are very much used in structural fabrications and so. So, that intercritical type of heat treatment is also used normally to have this dual phase kind of structure in many situations. Then next to that as we see, you have this is your partially transformed zone. Then below that also there are certain transformations taking place, and there basically you get the tempering zone, or also we call it as the zone of the spheroidized carbides. Now, in this zone the peak temperature will be from 550 to 750. So, it is below that lower critical temperature. So, below that and maybe from 600 to 700 normally what we see. So, now this is the extension of the partial transform zone just below that, And what happens that when you have little alpha to gamma transformation, then what we see in this case that there is spheroidization of the perlite. So, you get spheroidized particles of cementites. So, what you see is you see the spheroidal particles of Fe3C. So, since that heating rate is higher, so that breaks this lamellar structure of perlite, and then they will agglomerate, they will be having the formation of the spheroidal type of cementite, and that is why it is known as the spheroidized zone of spheroidized carbides. So, and this is normally occurring in the temperature range of 550 to 750 degrees C. So, that is seen next to the partially transformed zone. Then next to again adjacent to the this zone of spheroidized carbides, you have the zone of unchanged base metal. So, now here the temperature higher temperature reached is even smaller than 550. So, in fact, there is no considerable change in that as far as the morphological constituents are concerned, there is not much of the change, but you have the heat effect of heating, and then you have the residual stresses. So, basically sometimes there may be effect like strain, dynamic strain aging may occur also. So, in those ranges, because in that case you are heating, and then you have so, and there are residual stress developments also. So, they may interact, and there may be formation of the there may be presence of those situations where that is representing those dynamic strain aging behavior, because in that case there will be interaction of carbon and nitrogen atoms with the dislocations, and then that gives certain different type of behavior when the material is subjected to tensile loading or so. So, that is your dynamic strain aging, you must have the idea about it. So, that zone of unchanged base metal that is normally more prominent when you are using the multipass welt kind of thing. So, you have you are further you are so after certain time again it is so second pass and third pass if you are going. So, that region is subject to the changes, and that gives you this dynamic strain aging behavior. So, these are the different kinds of subdivision of the zones in the heat affected zone which we have talked about. So, you must have got some idea about these different zones based on the temperature, because they are all based on the different temperatures where the different reactions take place, and you have the different effect on the microstructure and further the mechanical properties. So, we will talk about the effect on the properties in the HAZ in our coming lecture. Thank you very much.